Nice introduction. So I will indeed give a talk about design and fabrication of polysaccharide cryogel beads for various applications, but I will also, towards the end, give a brief talk about topochemical engineering for the immobilization of Xylanase. First, I will briefly explain what our lab is doing. So we are chemical engineering for human health, which involves finding solutions for human health applications, involving, for instance, bone tissue engineering, development of drug delivery systems, or cell and gene therapy. And this is accomplished by using polysaccharides in order to create 3D structures like hydrogels, sponges, and microspheres, or alternatively 2D structures like films and coatings. Now to start, there is actually a bit of a conflicting definition regarding the concept of cryo and aerogels. So some researchers prefer to define these kinds of materials based on the drying methods. On this note, aerogels are any kind of gel which was dried using critical point drying. Cryogels are any kind of gels obtained through lyophilization, and xylogels are gels in which the fluid was evaporated from the gel. Now, according to the International Union of Pure and Applied Chemistry, they handle different definitions for these kinds of materials. So a xylogel is in this case an open network formed by the removal of all swelling agents from a gel. So basically this means that any kind of dried hydrogel is automatically a xylogel. And an aerogel is a special case of a xylogel in which the gel is comprised of a microporous solid in which the dispersed phase is a gas. And there is no definition for a cryogel. So these definitions make no comment on how the materials were fabricated. In my presentation, we will handle the definitions based on the drying methods. So the alginate beads, which is shown on the right, is actually obtained here through freeze drying, and we refer to it as a cryogel bead. So it is important in order to fabricate these kinds of materials that the homogeneous solution is prepared. Some polysaccharides are rather soluble, like carboxymethylcellulose, alginate, and starch, while others are soluble in simple organic solvents like ethyl cellulose or acetylated xylene. But cellulose is a little bit more complex, and this is due to the very strong hydrogen bonding, creating very strong inter and intramolecular interactions between the cellulose chains. So there are some cellulose solvent systems like the lyocell and the viscose process, which are able to completely dissolve cellulose. But both of these processes suffer from some drawbacks, which is why some alternative cellulose solvent systems have been proposed and continuously are being investigated. On this note, there is, for example, the use of aqueous alkali systems like the sodium hydroxide urea methods. Others prefer the use of ionic liquids, dipotectic solvents, the use of dimethylacetamides, lithium chloride systems, or alternatively metal complex systems, and recently also the use of aqueous quaternary ammonium hydroxides and salts. So regarding the use of these cellulose solvent systems, there are many concerns. For instance, regarding their toxicity. There are also some concerns regarding the degradation, as some cellulose solvents start to degrade over time. Some solvent systems require very high temperatures or very low temperatures in order to dissolve the cellulose. Some solvents are highly viscous even without the presence of cellulose, and so even the addition of cellulose to the solution will further raise viscosity. Some are also expensive. Some cellulose solvents are very sensitive to the presence of water, and even minor quantities of water in the solution can greatly impair the amount of cellulose you can dissolve. For instance, this is often the case in ionic liquids. And some cellulose solvents are also very limited in the total amount of cellulose they can dissolve. Now, what is interesting about these quaternary ammonium hydroxide systems like tetramethylphosphonium hydroxide and butyl ammonium hydroxide is that they are able to they are considered stable under moderate conditions. They can dissolve cellulose at room temperature, so there is no need for heating or cooling. The aqueous solutions themselves are non-viscous, and it is possible to dissolve high quantities of cellulose with moderate viscosities. And because we are working with an aqueous system, we also have not this issue of the water sensitivity. While the cost might be a small issue due to the higher cost of these kind of systems, it is possible to actually recycle the hydroxides. Now, to fabricate the gels, there are two approaches which can be adopted. In the first approach, the beads are the polymer solution is initially dispersed into an immiscible phase, which is then coagulated or chemically cross-linked, or alternatively, the polymer solution is dropwise added to a coagulant solution. And upon contact of the droplets, there will be a very fast gelation of the outer layer of the droplets, which will then start to act as a membrane, leading to mass transfer limitations. And therefore, the core of these gels tend to have a different kind of morphology compared to the skin layer. Now, different fabrication techniques can be adapted, like jet cutting, spinning drop atomization, or dripping, who will influence the particle size, diameter, and the shape. Now, before we dissolve the cellulose in the tetrabutylphosphonium hydroxide, we adapted the high-cell-solve pretreatment, which is basically pretreating the dissolving pulp in a mixture of ethanol and hydrochloric acids. This pretreatment is known to greatly lead to a controlled reduction in degree of polymerization, but it also improves the accessibility of the solvents towards the cellulose fibrils. The reason why ethanol is being employed in this process is because it leads to minimal formation of glucose, and it is known that the liquid can be recycled and be directly reused for an additional pretreatment of the next batch. So with this pre-treated pulp, we dissolved cellulose in various concentrations in tetrabutylphosphonium hydroxide. In the more diluted system, a white opaque paste was obtained, which could not really be employed for the fabrications of microspheres. But for the 40 and 50% solution, we obtained a clear and transparent solution. Next, we tested the viscosity of this solution in 50% tetrabutylphosphonium hydroxides, and we were only able to dissolve a limited amount of untreated pulp, up to 5 weight percent untreated pulp dissolved into the solution, and this had a viscosity of 10 Pascal seconds. But due to the pretreatment, we were able to reduce this viscosity to 0.2 Pascal seconds for 5% pretreated pulp. But we were also able to dissolve 10% pretreated pulp, and this viscosity was also lower compared to the 5% untreated pulp. And for the 15% pretreated pulp, we managed to dissolve it, but we noticed the clear indication of shear thinning, hinting that there is some undissolved cellulose agglomerates which remain present in the solution. So with this cellulose solutions, we prepared cellulose beads. And next, these particles were freeze-dried after the ethanol was replaced with water. So typically in freeze drying is that during the freezing step, and due to the expansion of water, this leads to the creation of large micropores, while much of the finer features in the gel are disrupted. Depending on the freezing conditions, for instance, very slow freezing, you get much larger crystals compared to a very fast freezing in liquid nitrogen, which tend to give a more abundant presence of ice crystal, which have a much smaller diameter. So once these particles were dropped in liquid nitrogen and freeze-dried, we obtained these cryogel cellulose beads. They are microporous as expected, but we also have very thick cell walls due to the high amount of cellulose which was present in the solution. So these were prepared using a 10% cellulose solution. A surface area we obtained in this case is 50 square meters per gram. To minimize this effects of the volume expansion of water, it is possible to add some cryoprotectants like sugars or polyethylene glycol, or alternatively, tetrahydrobutyl alcohol can be employed as the solvent, as it is an organic solvent with a high freezing point and a reduced surface tension. But what is particularly interesting in freeze drying are actually combinations of tetrahydrobutyl alcohol and water, as these mixtures upon freezing can form some very interesting morphologies. So around 20% and 19% TBA in water, there is a eutectic structure which forms, and in generally, under these conditions, it has been noted that this leads to much better retention of the porosity of the material. And in our case, this boosted the surface area of the gels to 218 square meters per gram. We also tested this in the past on cellulose beads, which were fabricated in sodium hydroxide urea systems. So on the left, we have the cross-section of a cellulose bead, and once again, we observe that there are very large micropores which are dominating the cross-section, but an overall lack of the much finer details compared to the other drying techniques. For instance, the freeze drying with tetrahydrobutyl alcohol, where we observe much finer details in the cross-section, and overall also a much larger surface area, up to 334 square meters per gram. The best technique to dry samples still remains critical point drying, in which we obtain the value of about 419 square meters per gram. And this can be attributed to the fact that this drying technique is also very suitable to retain the nanopores in the gel. So what we here propose is actually a new system in order to fabricate cellulose beads, in which we initially pre-treat the dissolving pulp in a controlled way so that we can influence the degree of polymerization, which will impact directly the viscosity of the solution, but also facilitate the dissolution process. Next, we can fabricate beads using various techniques, and it is possible to recover the ethanol and reconcentrate the tetrabutylphosphonium hydroxide back to 50%. And we actually demonstrated that it is possible to directly reuse this tetrabutylphosphonium hydroxide without any kind of purification. We can influence the porosity of the samples by the drying technique that is adopted, and what we get is then beads which can be used for a variety of applications, such as the development of sensors and electronics, for bioseparation and cell harvesting, for pharmaceutics and nutrition, in water purification, for moisture absorbance, in packaging, insulation, composites, abrasives, biocatalysis, and chromatography. But I will now talk a little bit more about the biocatalyst parts, because this is now the section about top chemical engineering and immobilized Xylanase systems. So the reason why enzymes are getting immobilized is because free enzymes tend to have a very limited lifetime, and we can extend this lifetime by immobilizing enzymes. So it's a mean of stabilization, but it can also increase the stability against more aggressive media, like much higher or lower pH values or much more elevated temperatures. We can influence also the selectivity of the enzyme towards certain products and substrates, and it enables continuous processing or facilitates recycling the enzyme activity. So while there are various methods which can be adopted to immobilize enzymes, like a carrier binding approach, a cross-linking approach, or an entrapment approach, we opted for a carrier binding approach, as the carrier itself actually has a particular influence on the enzyme function. So in the covalent carrier bond immobilization, we can make a distinction between the active groups, which are actively partaking in the formation of the covalent bonds. So this can be, for instance, aldehydes, which are present on the carrier, carbodiamide activated surfaces, or oxygenanes decorating the surface. And depending on the functionality of the surface, it can target specific amino acids on the protein exterior. There are secondary groups which are interacting with the protein through non-covalent interactions. They have a very important role during the initial adsorption, in which case they can even steer the orientation of enzymes towards a particular direction. But they also have a large impact on the stability of the enzymes. Last are the tethers, which also have this secondary group as a functionality, but they also play an important role in the dynamics of the protein. For example, if you have a very long tether, it leads to increased flexibility compared to multi-covalent attachment with a lot of very short tethers. So we decided to immobilize Xylanase as there are many interesting applications to xylan and its related products. The polymer itself can be employed as a thickener or an emulsifier or be added to animal feeds. If you completely hydrolyze xylan into xylose, the xylose can be used, for instance, for the fermentation and the furfural. But an incomplete hydrolysis leads to the formation of xyloligosaccharides, which can act as a prebiotic. If we talk about Xylanase, some actually refer to the crude xylan mixture, which is actually a combination of various enzymes which are required to fully break down these polysaccharides. But to obtain xyloligosaccharides, actually the most important one is endyl beta-1,4-xylanase. So prebiotics are actually very beneficial to human health, as they can boost proliferation and activity of beneficial communities in the gastrointestinal tract. The xyloligosaccharides are also a substrate in the fermentation of short-chain fatty acids, which have documented health benefits. They can also directly stimulate the immune system. They can mediate reactive oxygen species by acting as antioxidants and can affect fat levels in blood. Now, what we have noticed in general is that there is a trend in immobilized enzyme systems to produce mainly low DP xyloligosaccharides, meaning focus on the production of xylobiose and xylotriose, which is a bit surprising as these higher DP fractions also have the prebiotic function. So, for instance, a student of mine in the past, he immobilized cellulose, immobilized Xylanase on cellulose cutters and beads, and he used these particles for 5 consecutive runs. And he mainly produced xylobiose and xylotriose. However, upon each recycling, he lost part of the enzyme activity, and we noticed that there is then indeed a decrease in the xylobiose and xylotriose fractions, and a slight increase in the xylopentose and xylohexose fractions, but in general, the low DP fractions remain dominant. A second thing that we observed was that there was an overall lack of surface engineering, even though the enzymes themselves might be highly engineered. So what we decided to do in this work was to create a cellulose beads in which we activated the surface through pyruvate oxidation. We crafted different tethers on top of this particle, which differ in the chemical moiety in the center. And we checked whether these different tethers had a particular influence on the enzyme activity. And our intention was mainly to produce this higher DP fraction of xyloligosaccharides. So we did a pyruvate oxidation for different time frames, for 2 hours, 4 hours, and 8 of oxidation, which led to a variation in the aldehyde content from 0.1 aldehydes per anhydrous glucose units up to 0.7 aldehydes per anhydrous glucose units. And after this activation, the amines were attached, and we checked the presence using TOF-SIMS. We have the positive ion spectra for some particles over here, and we can clearly see the typical peaks which can be attributed to anhydrous glucose units are present at 127 and 145. And for the amine, we observe a peak at 106, and this matches actually parts of the amine due to the fragmentation. The activities of the enzymes were tested using the DNS assay, and the first observation was that a 4-hour oxidation gave better results compared to the shorter oxidation of 2 hours or the longer oxidation of 8 hours. So the reason for this can be that 2-hour oxidation was just insufficient to sufficiently functionalize the surface, meaning that there was less enzymes which was being bound on the particles, while an 8-hour oxidation might have led to excessive cross-linking, which will limit the activity of the enzymes. And if we then tested the particles which were activated using 4-hour oxidation and tested which sugars were being produced, we observed that we are indeed producing more of the high DP fraction like xylotetraose and xylohexose, so this was considered a big success. What was a bit surprising was the limited amount of xylopentose which was present. So either the xylopentose is preferentially broken down further to xylobiose and xylotriose, or the formation of this compound is somehow impaired, but we don't really know exactly why this is the case. So in conclusion, aqueous quaternary ammonium hydroxide are actually very interesting systems to dissolve cellulose, but also to fabricate gel beads. And tetramethyl alcohol is very beneficial in lyophilization to retain the pore structure. Prebiotics provide great aid to human health, and we observed that there was a general focus on low degree of polymerization oligosaccharides and a lack of surface engineering. So therefore, we created highly engineered surfaces with a focus on these high DP sugars. So I would like to thank my promoter Pedro Fardim and co-promoter Christophe Courtin, but I will also like to thank Arnaud Dacourt, in addition to Claude Polunis and Charlotte Schepper for their assistance to this work. And I also would like to thank some of the students who aided in this work. And on this note, I will end the presentation. Thank you for your attention, and I'm ready to answer your questions.